And that in the recorded video, I mentioned that plastic analysis is very important for you to be learned very well, because some of the subject after this that you learn is going to be based on plastic analysis. If you have a steel rod and you go to the lab and do tensile strength test, so what you're going to see from your test is most probably similar to this here for mild steel. So you're going to apply a force to your steel rod, and if you increase the force, basically you are increasing the stress, and at the same time the strain, which is the elongation inside your bar, is going to increase. So for a short period of time, you will see the relationship between stress and strain is linear. And after that, without increasing inside force, without increasing the applied force, you'll see that the elongation of the bar is increasing, which is the indication of yielding. And then after that, we have a strain hardening, that your bar steel resists the strain, the force that you apply, and finally it reaches rupture. So this is basically what we call it stress strain care for mild steel. Until now, the technique that you have learned so far is working on the elastic part of this curve, meaning where the stress and strain are having a linear relationship. So moment distribution technique, slope deflection technique, force method, all is basically they're all valid for the elastic part of this curve. However, structural elements, especially steel material, can tolerate much larger than this elastic range and can reach to higher stress. This is why the plastic analysis was developed, because if you use plastic analysis, your cross sections is going to have much smaller size, because we're using a higher stress in the design compared to the elastic analysis, which is always a coefficient of your yield, 60% to 70%, for example. And then we said, in order to understand better what's happening during the plastic analysis, we refer to a simply supported beam. We said we have a beam with a given cross-section, can be any shape. Here we have assumed to be similar to what you see on the screen. And then we said we are going to apply the force to the midspan, we increase it little by little. And then we will look into the stress distribution in the cross-section. We said when we are in the linear area, you can assume that the relationship between the stress distribution on top and bottom follows a linear line. And we can always calculate that basically stress using this equation, meaning the moment that you apply the force, you can calculate the bending moment. And if you want to know how much is the stress in any location of your cross-section, you just need to put it inside this equation. Bending moment multiplied by y is the location in the cross-section that you're interested to calculate the stress, and I is the moment of inertia of that cross-section. And then we said if you increase the force in the beam little by little, more and more fibers are going to reach to higher stress until the last fiber on top or at the bottom is going to reach to the yield stress. The moment that you reach to yield stress, then the stress is not going to increase, because according to the graph that just now we saw, by increasing the stress, only elongation inside your fiber is going to be larger. So at this time, basically, we have reached to the yield moment of our cross-section. So the yield moment can be always represented by this equation. So this equation is similar to the previous one. The only difference is that instead of sigma, we put sigma y. And then S is section modulus, which equals to I over C. So it explains sigma y multiplied by C divided by I. And C is basically the distance between the neutral axis and the outmost fiber. Again, we said if you increase that force in the beam, more and more fibers are going to reach to the yield until the time that the whole section's fiber have reached to the yield stage. So this is the time that we said we have reached to the plastic moment. And this is the maximum bending moment that your beam can carry. At the plastic condition, all fibers have been reached to yield stress. And if you want to calculate the plastic moment, you need to use this equation, which is Zp multiplied by sigma y, and Zp is plastic modulus. and can be calculated by the equations that is given to us. For example, for cross-section of rectangular sections, you use this equation. For circular one, you can use this section. In the video, I also explained that the ratio of MP, meaning plastic moment, to the yield moment, is called shape factor. And the larger is the shape factor, is better for our design because it gives us some alarm from the time that the structure yields and shows some crack until the time that it fails. So if someone is inside a building or it is a breach, people have more time to leave their structure because from the yield until the plastic time, when the structure fails, is going to be a larger distance. And then in the video, I'll mention that in order to calculate the critical load, which is the load that equals to the condition of collapse, we use a technique that equals the internal force to internal work to external work, and we call it kinematic approach. So if you have a beam and you want to know what is the ultimate force that it can carry before or at the time of failure, this is the time that you need to calculate the external work done by the wall, by the load that you have applied, and then you need to calculate the internal force done by the plastic hinge that form inside your structure, and equal these two and get the critical load. For example, in this beam, at the time of failure, the deflected shape of the beam is going to look like the one that you see in the right side. So when the load is increasing, the bending moment is going to increase until it reaches to plastic moment. So we said more than plastic moment is not possible because it's time that the structure is going to fail. And then if you remember in the video, we said that for a simply supported beam, in order to fail, we need to have 3 hinges in one span. So since in this beam, 2 supports are already working like a hinge because the bending moment over there is 0. So the moment that we get another hinge, which comes from the plastic condition inside the beam is going to reach to its failure condition. It said also we always assume that at the time of collapse, the deflected shape follows a linear condition, meaning we don't assume that there is a bending inside of our segments. So by these assumptions, at the time of failure, what we are going to have is a deflected shape like this one, in which we have one plastic hinge here, and this plastic hinge is exactly at the location that the bending moment is maximum. So the moment that we have reached to MP and plastic hinge form, we can calculate the internal work. Internal work is basically the bending moment at the plastic hinge, which equals to MP, multiplied by its rotation. Rotation of this plastic hinge, according to mathematical calculation, is always equals to summation of the rotation into internal angles, because this is a triangle right now. So the angle here, which is outside the triangle, is always equal to summation of 2 internal angles, which is far from the location of plastic hinge. So if here is rotation equals to theta, we assume it to be a theta. We don't know how much it is exactly. We assume to be theta. So at the plastic hinge, the rotation is going to be 2 theta, meaning from the horizontal condition, when the failure occurs, our beam is going to rotate in the location of plastic hinge 2 theta. So if you want to calculate the internal work, you just need to multiply this MP to 2 theta. And this is going to be the work done by the plastic hinge. We don't have any work done by the supports because at the support, there is no bending moment. Bending moment is 0. So 0 multiplied by theta is going to be 0. So no internal work is done. For the external work, it's always, work equals to force multiplied by displacement. So we assume that the beam at the time of collapse has a deflected shape of equal to delta here. So P multiplied by delta equals to external work done by this force. So this is what we have written here. P multiplied by delta is the external work, and MP, which is the bending moment at the time of failure, multiplied by 2 theta is the internal work. So according to kinematic approach, always internal work and external work should equal to each other. So if you make these two equal, from there you can calculate P critical. So you can see the P critical is 4 MP over L. That means at the time that this beam is going to collapse, the maximum force is going to reach to 4 times of MP. So this MP can be calculated for the cross section easily by the equation that just now I said, ZP multiplied by sigma Y. So if you want to have a safe beam, you need to provide 4 MP over L based on the force that you have. Let's say you have applied 100 kilonewton force here. So you can easily calculate how much MP you need to have inside your section. 100 multiplied by L divided by 4 is the MP that this beam should have, meaning the plastic moment of this beam shouldn't be smaller than that value in order to tolerate the 100 kilonewton force. Then we had more example in our slides. One of the examples that we observed was for the uniformly distributed force. We wanted to calculate the critical force that this beam is going to carry at the time of failure. We said the support condition here is fixed support. Therefore, if this beam wants to collapse, as we said, the rule is to have 3 hinges in one span. So since the support are not hinge or not roller, therefore, at the time of collapse, this beam is going to have 3 plastic hinges. And in order to determine where is the location of that plastic hinge, we said we need to look into the bending moment diagram. So this is the bending moment diagram of the beam. And if you look, you can see that the maximum bending moment occurs at the corners. And for the negative bending moment and for positive one is in the middle of a span. So therefore, if this beam wants to collapse, these 3 plastic hinges are going to be 2 at the both ends of the beam, and 1 is going to be in the middle of the span, because these are the locations that the bending moment increases more than other places. Therefore, the deflected shape of the beam at the time of collapse, again, is going to look like this one. But here we have 2 plastic hinges at both ends, unlike the previous example that there was no plastic hinge, it was only pin support and roller support. Okay, for here also, we can use the kinematic approach to calculate internal force and internal work and external work. For external work, again, is going to be the value of force multiplied by its deflection. Here, since the force is uniform, we have a little bit of modification in the calculation of external force. It's going to be W multiplied by L is going to be the point load equivalent to the total force, multiplied by the L, which is the deflection in the mid-span. But since the load is uniformly distributed, in order to take into account the effect of uniformly distributed load, we multiply the external work by 1/2. So W multiplied by L is the point load, multiplied by delta is going to be the work, and multiplied by 1/2, which is half of that work, is going to be the external work. So this 1/2 is only applied to the case we have uniform load, and it is to take into consideration of the distribution of force over the span. However, for the internal work, since right now we have 3 plastic hinges, so each one of these hinges is going to do some internal work for us. The first plastic hinge is having the bending moment of MP, so multiplied by its rotation, which is theta. We assume it to be theta. And the other side also is going to be theta because the beam is a symmetrical beam, and the loading also is symmetrical. Therefore, if one side is rotating theta, the other side also is going to rotate theta. So if this one is MP multiplied by theta, the other side also, the work which is done is MP multiplied by theta. The plastic hinge in the middle of the span, the rotation equals to 2 theta because according to mathematics, this rotation is equals to summation of these two. So we are going to have MP multiplied by 2 theta, MP multiplied by theta, MP multiplied by theta. So totally, the internal work is going to be MP multiplied by 4 theta. So if you make these two equal according to the kinematic approach, then you can get W equals to 16 MP/L/2. So if you want to know how much MP you should put inside your section, if W is clear for you, let's say W is 5 kilonewton per meter. So 5 multiplied by the length of your span power 2 divided by 16 is the MP that you should put for your section. So you need to design your section such that the MP is at least equal to this amount of value. So this was also another example of application of kinematic approach for the calculation of critical load. Okay, so today we are going to see more examples, and then you will see different conditions. So far, the two examples that just now we observed was for the cases that we had only one span. But in reality, there are many beams that are continuous. So it's not always the case that we have only one span. And the number of loads on the span also is not going to be always a single point load. Sometimes we have 2-point loads on the span. So we are going to see how we can deal with different conditions and how we can calculate the critical load. Okay, this is one example that I have put here. We have a continuous beam. One of the span doesn't have any point load. Another span has only 1 point load, and it is in the middle of a span. And another point load is having 1 point load, but in 1/3 of the span. So the location of the loads is not similar into two spans. And then the load that we have applied is similar, P and P. So the intensity of the force is the same. And another thing is that the cross-section area of the beams also are the same. When you see MP, 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 that means this span and this span and this span have the same cross-section. Because if the cross-section is not similar, the plastic moment is not going to be the same. But in the exam or in the next examples, you will see sometimes we have 2 MP here, 2 MP, and 1 MP. So some spans may have a larger size and some spans may have a small size. So you need to be careful about the size of the cross-section and do your calculation based on the MP which is given to you. Okay, what we want to do here, we want to determine the critical load for this continuous beam. In order to do that, if you have a multiple span, for each span you need to do the calculation separately. And you can calculate how much is the critical load for this span, how much is the critical load for this span, and then in order to see what is the critical load of the whole structure, the one that gives you the smallest value of P critical is going to be the critical load of all P. Because let's say if you get critical force for here 10 and for here 5, that means when the load is reaching to 5, this beam is going to collapse, although this span may not collapse. So that 5 is going to be the critical load for the whole beam because it's going to result in a partial collapse. So always keep in your mind that if you have a multiple beam and with multiple loads, span by span, you need to check, get the calculated critical load, and compare them with other span. The smallest critical load is the case that you need to announce it as the critical load for the whole beam. So this is what we are going to do right now. So first, we are going to look into the middle span and we calculate how much is going to be the critical load for this span. So if this span wants to collapse, as we said before this, we need to have 3 hinges. So these 3 hinges can be basically plastic hinge, or can be a condition in which we have roller or pin support. Now, when we are in the middle of the span, although we have 2 roller support here, but bending moment in this location and this location is not 0, because beam is a continuous beam. Therefore, if there is going to be a collapse inside this span, there should be 3 plastic hinges. And the location of these plastic hinges is very clear for us because bending moment and the supports is always maximum. And another location that the bending moment reaches to its maximum is the place that the force has been applied to the beam. So we are going to have 3 plastic hinges, one in the support, another one in the right support, and another one right under the load. And these 3 locations are the locations that the bending moment is largest compared to the other place. So the deflected shape of the collapse is going to look like the one that you see on the screen. And again, we have a linear condition between these 2 plastic hinges. And again, we are going to assume that the rotation of one side is theta. And since the load here is in the middle of the span, the rotation of other side is going to be also theta. Okay? And the rotation of the plastic hinge in the middle span equals to the summation of these 2 is going to be 2 theta. You can assume that the beam at the collapse time has a deflection of delta 1, for example. So we can easily calculate for this span what is the critical force. So this is the calculation that has been done. So internal work is MP. Don't forget here, the bending moment, the plastic moment is MP. So MP multiplied by this theta, MP multiplied by this theta, MP multiplied by 2 theta. So it is what we have written here. Okay? So internal work is 4 MP multiplied by theta. This is coming from the hinge 1, this is come from hinge 2, and this is come from hinge 3. And then for the external work is just the value of force multiplied by its deflection under the force. So it's going to be P critical multiplied by delta. But we said delta can be easily written based on theta, because from mathematics we know that if this one is delta and from here to here is L over 2, because the total length of a span is L. So from here to here is over L over 2. L over 2 multiplied by theta is always equals to delta. Therefore, I can replace the value of delta with theta. So this is what we have done here. Okay? So this is the equation that we have. Delta 1 equals to L over 2 multiplied by theta. This is for mathematics. So instead of putting P multiplied by delta 1, I put P multiplied by L over 2 multiplied by theta. Now, if external work equals to internal work, from there you get 8 MP over L. So if the force reaches to 8 MP over L, this span is going to collapse. Now, we need to do the calculation for the second span and get how much is the critical force for this span. So in this span, again, we need to have 3 hinges to make the span collapse. The right side of our beam is not continuous and has reached to a pin support. Therefore, one of the hinge, or the place that the bending moment is 0, is already there. So we need to have 2 more plastic hinges to make the beam collapse. One of the plastic hinge is going to be in the left side, because the bending moment here is maximum. And another one is under the load itself, because again, the bending moment is larger than the other place. So therefore, we are going to have 2 plastic hinge and 1 hinge from the support, rotor support, to make the beam collapse. So the deflected shape is going to look like the one that you see here. 1 plastic hinge is here, 1 plastic hinge is under the load, and the other side is only a roller that can easily rotate without having any bending moment. Okay, so always if you have pin or roller, keep in your mind that that one considered to be a hinge condition for you, and it can easily rotate without resisting again force. So right now our 3 hinges is already there. But the point here is, since the load has not been applied to the middle of the span, when one side is rotate theta, the other side does not rotate theta. It's going to rotate beta. Why? Because the beam is not carrying a symmetrical condition for the point load. So we assume that right side rotates theta, the left side rotates theta, and right side rotates beta. So the total rotation in the location of point load is always summation of these two. So it's going to be theta plus beta. Again, we can assume that at the condition of failure or collapse, the deflection under the load is delta. And you can easily calculate this delta based on theta and based on beta, because this one is L over 3. L over 3 multiplied by theta equals to delta. And 2L over 3 multiplied by beta equals to delta. So we can easily calculate theta based on beta. So they are easily can be converted based on each other from the mathematics. So this is what we have done. If you look to the calculation here, this delta 2 is equal to L over 3 multiplied by theta from the left side. And from right side, delta 2 equals to 2L over 3, which is this distance multiplied by beta. So from here, you can calculate how much is theta based on beta. Theta and beta are connected to each other, related to each other with this equation. So we can write down everything based on theta or everything based on beta. This way, the calculation will be more simple. Now, let's first calculate the internal force. So we are having MP as a plastic moment for this span, MP multiplied by theta, MP multiplied by beta, and MP multiplied by theta plus beta is the internal work. So here you may have a mistake, like now, like the one that I did just now. When you have a roller support or pin support, it doesn't do any internal work for us because at the beginning, this support cannot tolerate any bending moment. Therefore, when you are calculating the internal work, you are calculating only for the location that plastic hinge has occurred. The hinge condition that exists inside our structure doesn't do any internal work. Regardless it is a pin or roller, we don't have any internal work done by this support because bending moment here is 0. So 0 multiplied by theta is going to be 0 multiplied by beta is going to be 0. Therefore, the internal work that has been done is MP multiplied by theta and MP multiplied by theta plus beta. So this is what you see here. We don't have any MP multiplied by beta because here the plastic, the bending moment is 0. It's not reaching to MP. And now for the external work, we have P multiplied by delta 2. And delta 2 can be written based on this equation based on theta and beta. So finally, we can replace beta with theta and you can put inside the equation. If you make these two equal, from there you can get the P critical for the second span equals to 7.5 MP over L. So if you can compare these two, for the case that the load is applied in the middle of the span, we need a larger, it can reach to collapse when the load is larger. For example, if you calculate this one may equal to 10, this one can equal to 5. So this span is going to collapse when the force reaches to 5 kilonewton. This span is going to collapse when the force reaches to 10. And it is very clear that 5 kilonewton is a critical load for us because the moment that it reaches to 5, the right span is going to collapse. So shouldn't allow the force to reach to more than 5. So between these two, this is going to be the critical load because it is smaller than the other one. This is only one example of what's happening when you have a continuous beam and when you have point load on two different spans with different condition of allocation for the load. So as I said, you need to calculate for each span the critical load separately. And when you got the critical load, you need to compare them. The one which is the smallest one is the one that you use for calculation for the calculation of critical load. There is one more basically example here for you. Again, in this example, we have uniformly distributed load. But here the support condition is not both sides fixed. One side is fixed and one side is considered to be roller. So our job here again is to calculate the critical load that results in failure. So we want to calculate W critical. In this case, since the location of the supports are not symmetrical, so we know that one of the bending that can reach to one of the maximum bending moment is going to occur in the support A. But we don't know the exact location of bending moment for the positive side of these cantilever, this beam. So similar to what we said for other beams, for this beam, in order to reach to collapse condition, we need to have 3 hinges. So one of the hinges is already there because the support is roller. We need to have, therefore, 2 plastic hinge due to the increase in the force that makes the structure collapse. So these 2 plastic hinges should be determined. The location of these 2 plastic hinges should be determined. Of course, one of the location is going to be at the support A because the bending moment here is basically the largest. However, the location of the second plastic hinge cannot be easily distinguished. If you look at the bending moment diagram of this beam, it's going to look like similar to what you see. And the maximum one is going to occur somewhere between the moment of 0 and moment of 0 in the right side. At the beginning of analysis, we don't know exactly where is that maximum because the force is based on W, is not the exact value 10 or whatever. So our job is to determine where is the location of that maximum bending moment because this is the location that the second plastic hinge is going to form. So what we are going to do in this case is we assume that the location of the second plastic hinge is with the x from the right side. The distance is x from the right side of our support. So we are going to do our calculation based on that, and then we are going to determine how much is this x. I will see in the next slide. So if I want to repeat again, we have a beam, one side fixed, one side roller, and we want to calculate W critical. W critical, in order to be calculated, we need to see the deform shape at the failure condition. So for the failure of this beam, we need to have 3 hinges. One of the hinges is already here because bending moment here is 0. And then we need to have 2 more hinges. That is going to be due to the plastic hinge. So one is going to occur at point A, and another one is going to occur at the location of maximum positive bending moment. However, we don't know exactly where is that location. So we assume it to be the distance of x from the right side. And this is going to be the deflected shape of the beam at the time of collapse. So we have one plastic hinge here, one plastic hinge here. And since, again, the condition of the loading is not symmetrical, the supports condition is not symmetrical, therefore, when one side is rotating theta, the other side is going to rotate beta. And the total rotation is going to be theta plus beta. So again, we are going to use the internal work calculation equal to the external work in order to calculate how much is W critical. So this is what we have done in our next slide. So based on mathematics, I have calculated the delta based on theta and beta, like the previous example. So internal work is going to be MP multiplied by theta plus MP multiplied by theta plus beta. So this is coming from here. We have one plastic hinge, MP multiplied by theta, and MP multiplied by theta plus beta is going to be the internal work. And we don't have any work for the right side because it is the place that the bending moment is 0. So this is going to be the basically calculation of internal work. External work, like the previous example, is going to be W multiplied by L, is going to be the vertical load, and multiplied by its deflection. So if you look into my calculation, again, we have put this 1/2, which is going to be showing the average value of the condition when we have uniformly distributed load. So right now, we need to say internal work equals to external work. So if you do this calculation, you get this equation, MP multiplied by theta, MP multiplied by theta plus beta, which is internal work. And here, instead of beta, we can calculate how much is theta from the equation that we know. So we replace beta with theta, and then equals to, again, for delta also, we can calculate it based on theta. Just put the value based on theta. And after that, you can make a simplification and get MP equals to WL power 2 divided by 2 minus WLX divided by X divided by X over X plus L. So this is the basically value of MP that is needed for that beam in order to avoid any collapse. So you can see this value depends on X, and we need to calculate how much is that X. So in order to calculate the value of X, we are going to look into the deformed shape of our beam at the time of collapse. So if I go back to this diagram, okay, when the beam reaches to collapse, the bending moment here equals to MP. The bending moment here is also equals to MP. So you can easily cut this part of your beam from the left side and look into the free body diagram of your beam. And you can cut the right side and again look into the free body diagram. The moment that you cut it exactly at the location of the plastic hinge, the bending moment here is clear for you, that the value is MP. So you need to put that MP because you are in the collapse condition. So what we are talking right now about calculation of basically X is at the time of collapse. At the time of collapse, we need to know how much is this distance. So in order to do that, we know that at the time of collapse, bending moment here is equal to MP. Bending moment here also is equal to MP. And we can cut our beam at the location of X and look into the left side and right side and write some equations in order to calculate that value. So if you look into the left side, we have MP here, we have the load, and we have another MP over there. So you can write down sigma m at point A equals to 0, and from there you can write down MP WL multiplied by L minus X divided by 2 mod plus MP equals to 0, and then from there you get this MP. You can do the same calculation for the right side of the beam, which has been cut from the location of plastic hinge. Again, if you write down sigma m at point B equals to 0, from there you can get another MP. This MP and this MP should be equal because they have been cut from the same location. So if you equal this equation to this equation, you can get the value of X. So you can get the value of X, and you can put the value of X inside this equation, and then you can calculate how much MP you need for the cross-section in order to avoid collapse. Or you can easily calculate W here in order to calculate the critical load. And critical load equals to MP divided by this multiplied by L power 2. So for that beam, the basically critical condition is when MP reaches to this value. Or in other words, you need this amount of MP in order to avoid collapse due to the load of W. So this was also another example that the load condition is not, the support condition is not symmetrical, and therefore the location of plastic hinge is not occurring exactly in the midspan. So you need to see basically how you can get the MP based on W using the calculation that we just saw. So if you have any questions so far, you can ask. Otherwise, I will show you more examples. Any question? Okay, please ask the question.
Doctor, for the second diagram, MP square minus WX square over 2, is it the square is not square?
Which one? Which one here?
The second one, the right hand side one.
This one?
Yeah, the MP square, is it MP square?
Oh, no, 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 no.
Oh, okay.
No, it is a mistake here. It's just MP.
Okay, thank you, doctor.
Any other question? Okay. Let me see if you have understood the subject until now very well or not. So here, there is one example that I ask you to calculate. And after that, I will ask one of you to explain how is the calculation. So here we have a two-span beam, and then one of the span got a 20 kilonewton force, and one of the span got 15 kilonewton force. And the distance between the force is 2 meters, 2 meters, so loads are exactly in the middle of the span. So we want to calculate the critical value for MP. How much should be MP? The question says, consider a safety factor of 1.7, meaning you need to multiply these forces to 1.7 and then calculate MP. This way we are sure that if this load reaches to 70% larger than the value that is given, still the beam is not going to collapse. The answer is given to you 12.75. And right now I want you to think that how you can reach to this 12.75. So we have a beam, a continuous beam with two loads, 2-point loads, and we want to see how much is the critical MP for this structure. One point here is very important to understand, and you make always mistake in the exam especially. Sometimes we give you the force and we ask you to calculate how much MP should be. So if you want to calculate how much MP, you need to do span by span. You calculate SP for this span, you calculate MP for this span. And then, let's say for the first span, you got MP should be 10. For the second span, you got MP should be 12.75. So we're talking about MP. So if I ask you what is the critical value for MP, you should use the largest MP. largest MP. Sometimes you make mistake and you use the smallest MP. So this is different from the case where we ask you to calculate the critical force. If you want to calculate how much is the critical force, the smallest critical force that you obtain for each span should be announced as the critical force. But when it comes to MP, between the 2 or 3 spans that you have, the largest MP should be announced as a critical MP. Largest MP means the largest cross-section that you need. So if you calculate it, let's say for this span, you need to have a cross-section that can tolerate 10 kilonewton meter. And for this span, you obtain 12.75 kilonewton meter. If this beam shouldn't collapse, of course, you need to put the largest value of cross-section. Otherwise, if you use the smallest span, this span is going to collapse. So when you're calculating MP, you always use the largest MP. When you're calculating critical load for each span, you're going to use the smallest critical load span to announce it as the critical condition. So if it is P, you calculate P for each span, use the smallest. If it is MP, you calculate MP for each span, you announce the largest one as the critical one. Don't forget about this, because I can see in the exam, many students make mistake. MP, if you calculate for each span, the largest one is the critical one. P, if you calculate P instead of MP, so the smallest P is the critical force for the whole beam. Okay, now you have 10 minutes. I give you 10 minutes and I want you to calculate the critical MP for this beam. Okay, so let's see who has done the calculation. Anyone got the value of 12.75?
Yes, doctor, but I have a problem because my other MP was 17. So I think I made a mistake.
Oh, you got 17.
Yes, one of them was 17 and the other one was 12.75. So I think I made a mistake, but I don't know. What is it?
Oh, so you got one 12.75 and another one 17.
Yes.
Okay, so these two values have been obtained. Anyone else? Same doctor, okay. Okay, so, okay, same as bad, okay. Okay, so everyone got 12.75 and 17. So this the reason is that I ask you to do the calculation right now is that to understand that this value mistakenly has been written 12.75. So if you are calculating the critical value, you should put the largest one, that's 17, which is the largest of these two values for this span, and this span is going to be the critical value. So this was a mistake here, written here, and the largest value should be taken as the MP if it is 17, and the other one is 12.75, okay? Clear? Everyone understood? Okay, let's go and see more examples for the beam. These examples that just now we saw actually are the simple examples, and in the exam, normally we have a little bit more challenging questions for you. So two of those challenges is going to be explained through the examples that I'm going to present to you. So, okay. Okay, this is one of the questions given to the students in previous semesters. And you know that you have two compulsory questions to answer. One of them is moment distribution, a frame, and another one is coming from plastic analysis. Either it's going to be a beam or a frame. So this is one of the questions that was given to the students during previous semesters. So we have a beam here. One side is fixed, and another side has a cantilever part, new things. And then the span has 2 point loads. Span has 2 point loads. And we have also 1 point load located at the end of the cantilever part. In this beam, the whole beam has the same cross section because it is given MP and MP. So there is no difference between the cross section of first span and second span, which is the cantilever part. And the distance of the load is also given to us 2 meter, 2 meter, 3 meter, 2 meter. So the question first, normally in the exam, the first thing that we ask is to determine the number of collapse mechanisms that can occur. So this is something that you need to basically draw a diagram for it. The number of collapse mechanisms can occur. So if you have two span and you have only two, basically 1 point load in each span, of course you can say that it is going to be two collapse mechanisms. But right now, you have 2 point loads on one span, and you have also 1 point load in other span. So the number of collapse mechanisms that can occur basically is going to be more than 2. So this is something that we are going to discuss in this example. Here, in the first span, we said we always do the collapse mechanism study span by span. So if you first concentrate on the span that from one side is fixed and from another side is having a pin condition. So for this span, if the load is going to reach to its critical condition, we need to see where are the location that the beam is going to have plastic hinge. Before this, if you remember, we said we need to have 3 hinges for a span to collapse, okay? So same goes here. But when you have a cantilever part, you should understand that the cantilever part is not a continuous part, meaning there is no other support after here. So Basically, a cantilever condition is similar to having a pin condition over the end of the span. Meaning here, the moment that the beam collapses, it can easily rotate without generating any bending moment. So therefore, if this span wants to collapse, one of the hinges that can easily rotate is this location. It can easily rotate without resisting against the bending moment. And another two should be at the location that the load is giving us maximum bending moment. So one of them obviously is always in the fixed support, so it's going to be here. And the second one either can be under the 15 ton or it can be under the 20 ton. So we need to examine which one is giving us basically largest MP. So for this span, we have two different failure mechanisms that needs to be investigated. One of them is similar to what you can see here, meaning one plastic hinge occurs here at the location of maximum bending moment. Another one, we assume that it's going to occur under the point load of 15. And the second one is the pin support that we have that can easily rotate. Since it can rotate, the cantilever part at the collapse condition is going to move toward up. From the horizontal condition is going to rotate toward upward. So this is why we can say that there is no work done here and we can easily see free rotation. So we have basically two hinges, two plastic hinges, and one hinge here that can rotate. And the hinge has been assumed to be under the 15 ton. But this is not always the case. We may also have a collapse condition that the hinge is going to be under the 20 ton. So we need to examine that. That's why another case that can lead to the collapse of the first span is when one of the plastic hinge is in the support. Second one is this time, instead of under 15 ton, under 20 ton. And we have again rotation in the cantilever part. So this is going to be the second possible collapse mechanism that needs to be investigated. And again, for the same span, we may have another collapse mechanism. So in this collapse mechanism, instead of having one of the plastic hinge at the support, we may have one of them exactly under the 15 ton point load, another one under the 20 ton, and another one is going to be the pin support. Again, you see in the span, we have three hinges, one here, and another one here. So these are the three different cases that can occur for this span to collapse. And the one that is going to give us basically the largest MP is the one that is considered to be a critical case. Okay, so we are going to investigate all these three cases and calculate the MP and compare them. But in the second span, we have again a condition that may arise to collapse. And that condition can be the time that we have only one plastic hinge at the place that the support is there. If you look at the cantilever beam, you know that due to this cantilever condition, the bending moment here is always maximum. So in the cantilever condition, if you have only one hinge, one plastic hinge, your beam is going to collapse. Because if this is pin here, the beam is going to fall down. It cannot tolerate any bending moment. Therefore, the fourth possible collapse condition is the time that you have one plastic hinge right on top of the pin support. So it's going to be four possible collapse mechanisms. But we don't know which one is going to be the governing one, the dominant one. And that's why we need to investigate them all one by one. So this is what we are going to do. And we are going to do the calculation of internal work, external work, and equal them and calculate the MP. There is one point here. Always external work is equals to force multiplied by its displacement. Here, since we have a cantilever part, the displacement is in opposite direction of the force that has been applied. Force is toward down, but you can see the deformed shape, the beam is moving toward up. So if this force and deflection are not in the same direction, that work should be considered with negative sign inside your calculation. Here, these two is in the same direction of movement, but this one is in opposite direction. Therefore, the external force, the external work done by this 10-ton force, so 10 kilonewton, is going to be in opposite direction of displacement and considered to be a negative value. So now let's go and do the calculation. So I am not going to show you this mathematical calculation, but you can easily do it. This side rotates theta, the other side rotates beta. This one is delta 1, this one is delta 2, and of course delta 1 and delta 2 are not similar because we don't have a symmetrical condition. So we can easily from mathematics calculate that if this one is theta, from here to here is 2 meters, so the deflection is going to be 2 theta. And then if this one is theta and this one is beta, you can easily calculate theta based on beta. If you do the calculation, you will see that beta equals to 2/5 theta. So this from there, it has been calculated. You assume one side theta, one side beta, and then you can say that theta is equal to this 2 multiplied by theta equals to this theta, and 5 multiplied by this length equals to 2 theta. Then from there, you can calculate this value equals to 2/5 theta from mathematics. And then if this one is 2/5 theta, so the vertical displacement under the 20-ton force or 20 kilonewton force is 6/5 theta. So you see, I have written everything based on theta, but in the beginning of the calculation, you can do, as you can assume that this one is theta, this one is beta, and then calculate theta based on beta, and then other parameters all based on theta. Again, you need to see how much is the displacement in the right side where the 10 kilonewton force is there. So if you know this one is 2/5 theta, this one also is going to be 2/5 theta because they are a similar triangle. And then you can multiply it to the length and you can calculate how much is the displacement in the location of 10 kilonewton. 2 multiplied by 2/theta is going to be 4/5 theta because the length of cantilever is 2 meters. So do all the calculations based on theta, and this is what you are going to get. So if this one is theta, this one is 2/5 theta, you can easily calculate how much is the rotation in this plastic hinge, which is the summation of theta plus 2/5 theta. So now that everything is clear, we can calculate internal and external forces for this beam. So if you want to do the calculation, external work is 15 multiplied by its displacement, 2 theta, 20 multiplied by its deflection, 6/5 theta, and minus because this force is in opposite direction of displacement, 10 multiplied by 4/5 theta. So this is what you can see is calculated 46 theta. Now it comes to the internal work. So we have one plastic hinge here and one plastic hinge here. So these are the places that have done work for us. Other places, there is no work. Only the place that you see plastic hinge, work has been done. So MP multiplied by theta, and then MP multiplied by theta plus 2/5 theta. And then it's going to give you 2.5 MP theta. So if you equal external work to internal work, for the first span, you get MP equals to 19.17. So this is the plastic bending moment that you need in order to avoid this failure mechanism. If MP is equal to this failure mechanism is not going to occur. So we need to do the same calculation for the second failure mechanism. Here again, you assume one side is theta, one side is beta, and then you can calculate theta based on beta. And then this one is delta 1, this one is delta 2, and delta 1 and delta 2 can be calculated based on theta again. This is just a simple mathematical calculation. And again, the displacement at the place of 10 kilonewton also can be easily calculated from it. Now, let's calculate the external work. Is 15 multiplied by 2 theta, 20 multiplied by 4 theta, and again negative because 10 and the displacement over there is not in the same direction. So it's going to be 10 multiplied by 8/3 multiplied by theta. For the internal work, we have only MP multiplied by theta and MP multiplied by theta plus 4/3 theta, which is the rotation at that location. So this is what you can see has been done. So if you equal internal work to external work, you get 25 kilonewton meter. That means in order to avoid this collapse mechanism, you need to have a section that gives you 25 kilonewton meter MP. Now we go to the third one. The third condition is the time that we have plastic hinge, one under the 15 ton and another one under the 20 ton. And this is going to be the deflected shape. Again, one side can be assumed theta, the other side the angle is beta, and the vertical displacement is delta. So you can easily calculate delta equals to 2 theta and calculate beta based on theta. And again, calculate how much is the vertical displacement. And then internal work should equal to external work. Well, here there is one point. Since there is no deflection under the 15 ton, so 15 multiplied by the deflection, which is 0, equals to 0. So no external work has been done by this force because there is no movement under the load. Okay, so if there is no displacement under the force, its work equals to 0. Here we have 20 multiplied by 2 theta is a deflection, and then we have negative 10 multiplied by 4 over 3 theta. So this is what you can see over there. 15 multiplied by 0, 20 multiplied by 2 theta, and negative 10 multiplied by 4 over 3. Now it comes to the calculation of plastic rotations and internal work. So we have here MP multiplied by theta, MP multiplied by theta plus 2 over theta equals to this value. If you equal these two, you get MP equals to 10 kilonewton meter. That means you need to have a small cross section to avoid this failure mechanism. It only needs 10 kilonewton meter. Now we go to the last one, the fourth collapse mechanism. So here we have only one plastic hinge. Always, if you have a cantilever, one plastic hinge is enough for the failure. But if you have a beam with two supports, you need to have 3 hinges. Here, one hinge is enough. So internal work is MP multiplied by theta. External work is, this time is positive, 10 multiplied by 2 theta, because deflection is along the force that has been applied. So it's going to be 10 multiplied by 2 theta, and then MP multiplied by theta. So if you make them equal, in order to avoid this collapse mechanism, you need to have 20 kilonewton meter as MP. So now you have 4 MPs. 3 MPs are related to the first span or different collapse mechanism that can occur, and 20 kilonewton meter relates to the collapse mechanism of cantilever part. As we said, the largest value is the critical one, which is 25. So you need to have a beam that can provide at least 25 kilonewton meter to avoid collapse of this beam. And the number 2 is the time that can give you a real collapse condition. So this is the collapse condition that can occur because it requires a larger MP. So the other collapse condition will not occur because this is more critical than the other. So if this beam wants to collapse, is it going to collapse due to this case, not the other cases? Why? Because the MP that requires is larger than the other MPs. So right now, we know that this is the case that the collapse is going to occur, meaning at the time of collapse, the deflected shape of the beam more or less is going to look like this one. Sometimes in the exam, we ask you to draw the bending moment diagram at the time of collapse. So if you want to do bending moment derivation, you need to know that you are driving it at the time where the collapse is going to occur. So at the time where the collapse is going to occur, the deflected shape of your beam is look like the one that you see here, meaning you have 2 plastic hinges inside your beam. One plastic hinge is going to be at the place of 20 kilonewton force, and another one is going to be at the location of support, according to the value that you have calculated. Okay, so this is the deflected shape, and this is the location of plastic hinge. As we said, when the collapse occurs, the bending moment in the plastic hinges are clear for us. So we know that how much is the bending moment here and how much is bending moment here. So you know the bending moment here, you know the bending moment here. Therefore, at the time of collapse, you know that this is your beam. You know that at this location you have 25 kilonewton meter bending moment here, and another 25 kilonewton meter bending moment here. Always the direction of this bending moment inside your plastic hinge in the opposite direction of displacement that occur during the collapse time. Since the beam wants to go down, so the direction of bending moment in the plastic hinge is in the condition that wants to bring up the beam to its original condition. So this is the way that you can understand how it should be the direction of your bending moment at the plastic hinge. So look into the deflected shape of your beam and put the bending moment in the direction that wants to bring it to the original condition, because it resists against the collapse. So the direction should be in such a condition that the beam doesn't fall down. So it wants to push it up. And similarly, since this one wants to rotate down, the bending moment wants to bring it back to the original condition. So this is basically the free body diagram of your beam at the time of collapse. So if you want to calculate the bending moment or support reaction and everything, it's very easy, because you know the values and you can just easily cut it from the location of your interest. Write down sigma Fy equals to 0, sigma M equals to 0, and calculate support reactions. And then after support reaction are clear, you can easily draw the bending moment diagram. So this is what we have done. First, I have cut it from the plastic hinge and look into this part. I have a 25 kilonewton meter bending moment over there because plastic hinge has formed. I don't know how much is the shear force. I don't know how much is the support reaction. So I can easily write down sigma M at this location equals to 0. I can calculate the RV. Then sigma Phi equals to 0. I can calculate VE. So I have done it. This value are there. So right now that I know this one, I can draw the bending moment diagram. So here 10 multiplied by 2, negative 20 is the bending moment over there. Bending moment in the location of plastic hinge equals to the plastic moment that we calculate, 25. And then from there, it reached again to 25 because, again, the bending moment is the value of plastic hinge calculation. So you just linearly connect them to each other. And the direction is based on the direction that you need to know the positive sign and negative sign of bending moment. So you can easily draw the bending moment diagram at the time of collapse. Okay, before I go to the second example, please let me know if you have any question. Yes?
Is it possible the plastic hinge to be at the fixed end at the force 15 and the force 20?
Meaning we have one here and one here and one here? Can you let me know that in what location you mean the plastic hinge? Right now, one of the plastic hinge is in the support. So another one can be either under 15 or under 20. So this is why we have two different cases. Always the plastic hinge location is at the place that bending moment is maximum. So we know bending moment in the support is always the largest. So one of them is going to be there. But the second one, we don't know where it is. It can be under the 15, it can be under the 20. So that's why we investigated two different cases, one under the 15 and one under the 20. Okay? And then we said, yes.
So it will not be possible at the 15 and 20 at the same time.
Okay, you may investigate, but it's going to be four hinges, because one here, and one here, and this one also is hinge. So it's not possible to have four hinges. As I said, when your spine wants to collapse, the minimum hinge for collapse is 3. Meaning, if it reached to 3, it's already collapsed. So you don't need to search for the fourth one. Therefore, you need to look at your span and see how many hinges is already there. So since this is a pin support and it is a cantilever one, if it was a continuous, it was a totally different story. Since it is a cantilever, it can rotate. So one of the hinges there, you need to have two more hinges.
Okay.
So these two more hinges, one of them is in the support, one of them under this load. Okay, so if you say one here, and one here, that means you have 4 hinges because one of them is already there and another 3 you are making.
Oh, okay. Understand. Thank you.
Okay.
Yes, yes.
Okay, any other question? You can examine all possible cases that comes to your mind, and at the end of the day, the cases that are not valid are going to be removed when you compare them with other cases. So what I want to say is that if you knew the bending moment diagram of this beam at the first place, you could always say that this is the only case which can be possible for the collapse, because plastic hinge always occurs at the place that the bending moment is maximum. But since it is an indeterminate beam, so you don't know exactly where is the location of maximum bending moment. It's here or here or here. Of course, support is always maximum, but under these two loads, we don't know. So that's why we examined 3 different cases to investigate which one is going to give us the critical MP. So we can investigate all possible cases, but with these rules that if you have a beam, 3 hinge is enough for making it collapse. So you need to search for the location of those hinges. If your support or pin or roller, so one of them or 2 of them is already there. So you need to search for the location of plastic hinges. And then when you got 3, then you can examine the value of MP. Okay, if there is no other question, we can look into the second example for beams. No question? Okay, hopefully you have learned it well. This is another question. In this question, again, we have a fixed support and we have 2 spans. One span has only 20 kilonewton force, and the second span has 2 point loads, 115 and 110. But in this example, the cross-section size of our beam is not similar. The first span has 2 MP, meaning it has a larger size compared to the second span that has MP. It's very normal and common that in the exam, you will see that these MPs are not similar in one span compared to other span. That doesn't change anything, only when you are calculating the internal force, internal works, you need to use the values that is given to you for that span. There is only one important point here that often you make mistake during the exam time, and I will explain it during the time that we solve the problem. Okay, since this is a 2-span beam, what we are going to do is again go and investigate the cases one by one. So for this beam, we have a failure mechanism for the first span and failure mechanisms for the second span that need to be investigated. So the first part of the question is again asking what are the possible failure mechanisms. So since the first span is having a fixed support and it is also a continuous beam, so we need to have 3 hinges here because there is no any pin condition or any cantilever condition. So these hinges, one of them is going to be at the support, one of them is going to be under the point load, and another one is going to be on the right support. So this is going to be one of the collapse mechanisms that can be possible. 3 plastic hinges needed because we don't have any pin or roller support, and the beam is continuous. Now we go to the second span. In the second span, we have to examine several cases. One of the cases is when, first of all, you should know that this span has 1 roller support in the right side. So since one of the support is already roller, in this span, we need to have only 2 plastic hinges to make the beam collapse. And now we need to investigate where are the locations that be possible. One of the location is always the support. So one of the plastic hinge is going to occur here in the support. One hinge we have here, and another one either can be under the 15 or under the 10 kilonewton force. So it gives us 2 different cases. One hinge is here on the support, another one is under the 15, and we have a roller hinge. And the second case is when one hinge is here, one is under the 10, and another one is the hinge condition. You may say that, okay, why not we examine another case in which, let's say, one hinge is here and one hinge is here when we have a roller condition, maybe something like this, for example. Something like this. You can examine, but definitely you are going to get a value which is not going to be a dominant one, because it's not possible that you have a very large bending moment here and here. The bending moment always in the support is larger than the bending moment under the load. But you can always examine it, and if you got a value, you can compare it with the other cases. But by experience, we know that it will not occur that way. Okay, so support is always one of the locations that needs plastic hinge, especially when your beam is continuous beam. And if the other side is roller, we don't have any plastic hinge there because it's already placed that the bending moment is 0. So we have 3 cases to examine, 3 different collapse mechanisms. So the first one is the time that the 20 kilonewton force has been applied to the middle of a span. So since it is in the middle of a span, this side, it rotates theta, the other side is going to rotate theta. Deflection can be assumed to be delta. the point that you need to understand here is the value of MPs. So this span has 2 MP. You can assume it to be a beam like this shape. Okay, so here is 2 MP, here is 1 MP. And let's say this is our support, and this is the fixed support that we have, and this is another support. This side of our beam is larger than this side. So when you are calculating the MPs at the plastic hinge, you should understand that when a plastic hinge falls between a large beam and a small beam, you need to always assume that the plastic hinge at this location can reach only 2 MP, not 2 MP. Because if you apply force to this beam, the moment that the bending moment here reaches 2 MP is going to crack, because this beam has been weakened. The size gets smaller. So at the location, at the boundary between these 2 MP and MP, bending moment maximum can reach 2 MP because beam is smaller in terms of size. However, for the right side, like now here or here, the bending moment can reach to 2 MP at the time that the beam collapses. So this needs to be understood very well when you're calculating the internal works. So right now in this beam, you can see that when I have drawn the condition for collapse, I have written here 2 MP because 2 MP is given for the cross-section size of the left span. And then under the beam also is 2 MP. The bending moment can reach to 2 MP. But right side, since it is the boundary between 2 MP and MP, we consider always the smallest one. So if here was 3 MP, 2 MP, we put here 2 MP. If it was 5 MP, 3 MP, we consider 3 MP. Okay, so right now we have 2 MP and 1 MP. Therefore, the bending moment there can reach 2 MP because of this case that I explained right now. Before reaching to 2 MP, the beam has already collapsed and reached to its ultimate capacity. So right now, you can calculate the internal work. So it's going to be 2 MP multiplied by theta, 2 MP multiplied by theta plus theta, and MP multiplied by theta. So this is the internal work. External work is 10 multiplied by delta, and again, you can write delta based on theta, make them equal to each other, and you can get the MP for this case. And then when it comes to the second case, again, you have different deflection under each load. This one is delta 1, this one is delta 2. And since the beam is not symmetrical, so rotation in the left side and right side are not the same. So you can calculate how much is theta based on beta and put it inside the equation. This is what I have done. Delta 1 is 4 theta, delta 2 is 5 beta, and then from there where we can calculate delta 1 over delta 2, and you can write everything based on theta. So you calculate internal work, which is again here between these two. The smallest value is MP, so that's why we put MP. MP multiplied by theta, and the span itself is MP, so MP multiplied by theta plus beta, and MP multiplied. Okay, since here again we have a roller, there is no work done here. Often you make mistake and you write down also MP multiplied by theta, beta, but always keep in your mind if you have a roller or pin support, since bending moment is 0, so 0 multiplied by beta is going to be 0. Okay, for the second span, for the second basically case, we got 33.093. And then the last case is the time that hinge is under the 10 kilonewton force. So the calculation is similar to the previous one. It just changed the value of delta 1 and delta 2. And for that one, you get 40. So you see, we have here 40, 33, and also 17. So the critical condition for us is the maximum of these 3 values that we obtain. Meaning we need to have a cross section that gives us at least 40 kilonewton meter bending moment. So if the resistance of the cross section is 40, the collapse is not going to occur. So 40 is the critical MP for us. And if you want to draw the bending moment diagram also, again, you need to look into the collapse condition. At the collapse condition, you have 2 plastic hinge, one here and here, and the value of bending moment is how much? Is 40. So you have 40 here and 40 here. And the direction of bending moment also is in the direction that wants to bring the beam back to its original condition. So for the right side, it's going to be counterclockwise, clockwise, and for the left side, it's going to be counterclockwise. And here also, you are going to have the counterclockwise direction. So this is the direction of bending moment. So again, you can cut your beam from the location of plastic hinge. Write down sigma m equals to 0. You can calculate the support reaction. And again, you can cut it from the other part. Again, calculate the support reactions and then draw the bending moment diagram. So this is another example which was given to the students during previous semesters. If you have any question, you can ask. Otherwise, we can have 10 minutes of rest and then we can continue with our discussion. Any questions so far? Any question? If you have a question, please open your mic and ask the question. Okay, so since there is no question, we come back at 12. Right now it's almost 40. 12:50. 12:50, we continue.